Good morning. Welcome to Unit 2, Organic Chemistry. I am phenomenally excited for today's video. I want to break apart this topic into 3 separate videos to try to keep them reasonably length. And our topic for Unit 2, we're going to have 3 different topics. This topic I'm going to call stereocenters, and we're going to get to that vocab in just a minute. But what's awesome about this topic is that there's actually a rich history behind this whole topic of stereocenters. And why do we care? Whether you're a chem major or a bio major or heading into healthcare, this has serious ramifications for all of us in chemistry and biology, and frankly in the world that we live in. If you've ever taken a drug, this is something you've got to think about. And so what I've done in this video, this first video is going to be largely the history of stereocenters. And I'm really excited to put this together because unfortunately, this has a rich history in the last 200 years, which is awesome because it's a really cool story to tell, but it's also has a downside, which means the vocab is actually quite intense and it's been evolving over time. So I thought one of the best ways we could present this material is start with a video that kind of takes us through that journey and that history. Now, when you're taking your test for me, we're going to be very application heavy, but I want you to know where all of this is coming from. So I kind of want this video to be background, but also be informative. And I want it to explain why we have so much vocab in this unit. And then our second 2 videos will be all about the application. So on our exams and our homework, we're going to be very application heavy. I'm just going to use the vocab in our questions. So I'm not going to necessarily ask you a ton of vocab except on your quizzes, but we're just going to apply all of this language. So because we've gone 0 textbook, I put your links to your textbook in here for stereocenters. And again, it's whether or not that is helpful to you. Here are the links for those websites to your OpenStax books. You don't have to use all of them. I just included several. I don't want it to be overwhelming. I just wanted to give you options. And then, of course, any OChem textbook is going to have an entire chapter on just stereocenters. So I personally like a textbook chapter. But in case you don't have a textbook, here's some links. And then today's journey has several Nobel Prizes in chemistry. So I went ahead and gave the general link just to Nobel Prizes in chemistry. It's just a really awesome resource. I wouldn't want you to feel like you need to know that whole website, but I'm going to cite several people today that have won Nobel Prizes in chemistry for their work on stereocenters. So this is just a really cool link. If you're ever curious what the Nobel Prizes in chemistry are, there they are. You can also look at biology there. They've got both. All right, we're going to start our historical journey with one of my favorite topics, booze. All right, let's just talk turkey. So if we're looking at booze a couple hundred years ago, we had a couple common, forms of booze, but certainly throughout the last thousands of years, wine has been a pretty popular option for booze. It's been around forever. I would have to hazard a guess, a couple thousand years for wine. So our journey in chemistry actually starts there. And what's really fun is that an awful lot of breweries and vineyards and a lot of booze places actually have organic chemists on staff. It is an area of chemistry for organic chemistry. So studies of wine back in the day in the early 1800s started with a compound called tartaric acid. And they would get it literally, it would be crystals left behind in wine barrels. And so It sounds pretty silly, but it's pretty fascinating that that would be an actual topic of chemistry. Why not? Chemists are just curious about the whole world around them, and if they enjoy a glass of wine, I'm sure they're going to get real sassy and wonder, I wonder where those crystals are coming from, and what are they? Isn't that awesome? So looking at tartaric acid, let me give the generic structure. An entire area of chemistry started with the study of tartaric acid. I'm going to go ahead and draw lactic acid as well, because they're actually a little bit similar and they've got some rich history there. All right, so our lactic acid All right, so let's focus on our tartaric acid, and it's sometimes called tartrate. And we know that is if this is the salt. So we can have both forms in wine. Those salts left behind form really nice crystals, and an awful lot of chemistry is coming from that. I included a really fun article here. It's an actual real article, and it's starting to look at tartaric acid and taking you through that journey. So let's mark that that's for fun. Most of the links in this video are not meant to be overwhelming. They're just meant to be fun if this is something you find interesting. So going all the way back to these wine barrels, they noticed these crystals in these wine barrels. And what's pretty cool is that an awful lot of chemistry for the next 100 years studied those crystals from those wine barrels. And in about 1815, a French physicist and chemist, Jean Boit, actually looked at those crystals. And he looked at several crystals, and he discovered something called optical rotation and polarized light. So he was just fascinated with light and rotating light, and what he discovered way back in the early 1800s is that there are naturally occurring organic substances like tartaric acid that actually rotate light. And that sounds really silly, but if you think about physics in the early 1800s and chemistry, just to figure out that you can actually polarize and rotate light is a really major feat, just even in and of itself. So he was actually quite famous and did an awful lot of work with the rotation of light. I want to comment here that an awful lot of our vocab starts here, and it is with the polarization and the rotating of light and something called optical activity. And we will get optical activity just a little bit later. We're going to get a little bit deeper with that. And what's cool is that when you started to look at these organic substances, some rotated light clockwise, others rotated light counterclockwise. So the plot just thickened. And if I had any clue how to make these videos and put in music, I would put in the, like dun dun dun. The plot just thickened. We have optical rotation. So it turns out that our substances, whatever it is, so let's take your wine glass. Oh, let's draw a fun visual. Okay, I've got some booze in my wine glass. And oh my gosh, my light coming out is rotating either clockwise or counterclockwise. Now, what's deep in this is really two things. Number one, that they rotate light at all. And then number two, sweet Jesus, some of those compounds rotate in one direction, some of them in the other. Okay, now that's pretty deep. How in the world does that even happen? What's awesome is that it really took almost 50 years for people to really start to figure out how that even happens. So around the same time, early 1800s, another physicist, Vant Hoff, started looking at this exact same experiment. If I'm going to take tartaric acid, take my little wine glass, and start passing light, polarized light through that substance, And then how in the world could that even rotate light one way or the other? So he really wanted to start to study this mystery. It was a really big mystery at the time. And he came up with an idea that there must be some kind of asymmetry in that substance. So there must be something that's not symmetrical. So basically no symmetry in that substance. And he brought back in this idea, well, wait a second, could that have to do with tetrahedral carbon? Remember, still at that time, they did understand that our carbon would be nice and evenly spaced and have that tetrahedral geometry. So he kind of started to make the connection, well, wait a second, there must be something that's lacking symmetry, and could that be tetrahedral carbons? In fact, he went the next step and had a general idea that maybe it kind of could depend on how many of those carbons might be in that substance. And modern day, we give credit and we use something called the Vant Hoff rule, which is going to tell us how many of those stereo isomers are possible. So let's mark this down as modern. We are going to keep this, and we're going to add this. This is the Vant Hoff rule. We're going to add that to our vocab at the bottom of this video. We're going to make a big chart of vocab. So we are going to use the Vant Hoff rule, and we'll use it when we get a little bit farther in our vocab. And we're going to keep this idea of asymmetry. We're going to have a lot of vocab that deals with the fact that there must be some asymmetry and some tetrahedral carbons in there. That's coming from Vant Hoff's work in the early 1800s. And then as the plot thickens, our mystery is starting to unfold. We get someone that I hope, oh my gosh, how could I spell that name wrong? I forgot a letter there. As we get rolling, now we're hitting the mid-1800s, and somebody we've all heard the name for, Louis Pasteur, is actually famous for several things, but to an organic chemist, it is his large body of work with tartaric acid and optical activity and optical rotation. So what he did was take those crystals and get even deeper with this idea of rotating light, biological activity, he got much deeper with these ideas. So what did he do? He did two huge things. He did a whole lot of studies, two that we're really going to see modern day. So I gave a couple links, just Wikipedia if you want to see his picture and a little bit of his background. But what's really cool is back in 2017, New York Times published a whole article just on Louis Pasteur and chirality. That is fun. You really should just take a look at that. That is a super fun article. So two major things to summarize in our video. The first one is he took the actual crystals of that tartaric acid and he looked at the actual shape of the crystal. He got even deeper. He took those shapes of those crystals and he noticed, wait a second, there's actually mirror images in here. And he literally took a tweezer. He grew crystals and he separated by shape. So he literally took a little crystal tweezers and he separated by each of those crystals' shape. This is phenomenally deep because it ties into his second observation, and then we'll put them all together. And that is when he noticed from living sources, the tartaric acid rotated light. But from chemical synthesis, it did not. Okay, this is huge. We are going to have a whole lot of vocab here. In fact, two of our terms are coming right from here. We have optically active for things that are rotating light, And then we're going to have this idea of a racemic mixture, something that does not rotate light, but has asymmetry. So a lot of this vocab really started in the mid to 1800s. And what he found was fascinating. Not only did he find that the tartaric acid from a living source rotated light, and from chemical synthesis it didn't. What? He also found, and I put this quote in because I love it, that he was in the lab and made a mistake. I love it. This is where so many major discoveries come from. And he found that if he took that tartrate salt, it turned out that there was biological activity here and biological selectivity. Microorganisms consumed one of those shapes of crystals and not the other. Okay, this is phenomenal. For 1860, this is a huge conclusion. What it means is sometimes in nature, there is a preference. And nature can give one rotation over the other, and it can also consume one rotation over the other. So there's a whole lot of vocab that is coming from here. We've got close to 50, 60 years of studying now. And how can you tell the difference between the two? You can see which direction they rotate light. That is our little pluses and minuses. And then he literally looked at the crystals and their shape. So he correlated, well, wait a second, one of those shapes rotates light this way, the other shape rotates light the other way. This is huge. A lot of information about our Mother Nature and molecules came from these observations. And we started to look at the fact that molecules themselves have some place that they have asymmetry, and that they can rotate light or not. Okay, huge. And then as we fast forward, because this is still such a mystery, how in the world is this happening? Why can some compounds rotate light if they came from nature, but the same compound in the lab did not rotate light? Are they different compounds, or are they different shapes, or what happened there? Okay, so then as we work our way through, in the late 1800s, Lord Kelvin of the temperature Kelvin came up with this idea of chirality, meaning from the Greek term for handedness. So what if you have a molecule that's like a right hand and a left hand? Maybe the right-handed molecule can rotate light this way. Maybe your left-handed molecule rotates light this way. And if you have only right-handed molecules, you'll rotate light. If you have only left-handed molecules, you'll rotate light in the other direction. But wait for it, what if you have a 50-50 mixture of both? Well, now you have the exact same compounds, right? Only even if you rotate light one direction, the other half is going to rotate it right back. So this is called our racemic mixture. We still have asymmetry. We still have that tetrahedral carbon. We still have both shapes. But if you have an even mixture of both, this will not be optically active. Okay, so this is going to be a big vocab that we're going to use quite a bit. You have to actually have only the right hand and you can rotate light one direction. Only the left hand gives you the other direction. But if you have an even mixture of both, now it's not optically active. So this actually explains a little bit. It turns out that Mother Nature will really prefer one over the other. So when something comes from nature, it can rotate light. And then if you make it in the lab, you're going to get an even mixture of both. and that does not rotate light. All right, so by the late 1800s to early 1900s, they've got a way for looking at these crystals. They've got a way to actually test if something is optically active. And then they're picturing and they're getting to a place where they're correlating that with our sp3 carbon. Emil Fischer also won a Nobel Prize in chemistry. This was in the early 1900s. I think he won his Nobel Prize in 1902. He started to connect and try to draw a way of our sp3 carbons in order to show that they might have a different shape. So he came up with something called a Fischer projection. You will see these a lot in biology. He came up with a Fischer projection to show that sp3 carbon, and to show that you might have a mirror image within your compound. If you can take and switch two of your ligands, these are actually different. Their symmetry and their properties, one would rotate light one way and the other one would rotate light the other way. So you'll see a flat cross-like, that is a Fischer projection. But keep in mind, this is back in the day that they did not have drawing programs or a way to give a wedged and a dashed. So they essentially took something that is 3D structure based, like a crystal, and made it flat. So you'll still see these in sugars because they're easier to draw and memorize, but they are not actually relevant to your 3D shape, and amino acids. And the reason these work for sugars and amino acids is they have a set of rules, and they have two groups that are always consistent. So for an amino acid, you have an amine and you have an acid always. So you can always keep those two the same, and then you're just looking at swapping the other two groups. Same with sugars. So in my class, we don't do Fischer projections until we hit sugars and amino acids. You will read in a lot of textbooks, they're using Fischer projections for everything. I personally hate that. It's very confusing and it's not the best way to do it. This is old vocab, and it's really the best when it's only used for sugars and amino acids. Again, because you have two groups that are always the same, so you can just alternate the other two, and it's a quick way to draw them. So we won't actually use these. We will wait until OChem 2. All right, so let's fast forward just a little bit. So we're getting into the early 1900s. What's awesome now, just throwing in a little bit of tidbits. You guys, this is the coolest link ever. If you are fascinated by the pharmaceutical regulations and FDA, I personally have been trained, I worked in a pharmaceutical company in the FDA side, so I've been personally trained on the FDA regulations. And what's fascinating is their rich history and how chemistry has really shaped a lot of the FDA policies and back and forth. And so starting in 1906, now that we're getting into these organic substances, now they're starting to be regulated by the FDA. So drugs and vaccinations are now regulated by the FDA. And just for funsies, I put in penicillin. So FDA had to really adjust here with the whole polio. Okay, so now processes on our systems are validated through the FDA because literally 236 people were given polio instead of the vaccination because of, as I understand it, they needed to cool or heat. I think they incubate the vaccination so that they kill it, and that process didn't reach the right temperature, and they ended up giving people polio instead of vaccinating them. So this process is, all of this is now regulated. So that's pretty fun if you're on the bio side. For us in chemistry and our stereo centers, this is a big one. In the 1960s, a drug for pregnant women came out, and that was thalidomide. Thalidomide itself has a stereo center. In other words, we have an sp3 carbon and asymmetry. And that drug was marketed, if I'm not mistaken, as the 50-50 mixture we talked about, the racemate. Only remember what we learned from Louis Pasteur. In an awful lot of these situations, one of them has a particular bioactivity. The other one might be different. So starting in the 60s, this was a hard lesson to learn. But what happened with thalidomide is that one of those 3D structures, this is where we're headed, one of those crystals, if you were to crystallize it, actually prevented nausea in pregnant women and was used as, I think, a sleep aid. The other one caused severe birth defects. So starting in the 1960s, heavy regulation started on drugs, and a whole area of chemistry and chirality really had to up its game, because what's happening is that nowhere in there have we correlated structure yet. We have only talked about rotating light. There is no connection to rotating light and 3D structure. What I mean by that is that you can't say that something that rotates light to the right will always have, this structure. You can't say that. That is up to Mother Nature, not up to you. So as of the 1960s with the thalidomide babies, this whole area was really calling for a way that could be very specific in connecting 3D structure to that optical activity, or literally to that bioactivity and all the important part of that. But there was no correlation yet between the actual structure, rotating light, and that bioactivity. So along comes Vladimir Prelog, and in 1966, he really got deep with this chirality again and that right-handedness, especially after the incident with the thalidomide babies. So he got a little bit deeper, and this is where a lot of our modern terms are going to come from. And it is now looking at mirror images, rotation, no symmetry, and really that mirror images, you cannot have a mirror image within your compound. You have to have mirror images in your two compounds. And I'm going to add a vocab word here, but it's going to be very prevalent in our next couple of videos. I need my last video to explain it. We're going to look at something called meso. And now what's awesome is starting in 1966, a whole system came out to designate and correlate structure, our 3D structure, to our other properties. And that designation is from the Kahn-Ingold Prelog, and that is the RNS system. That is the system that we will use. From 1966 on, this is the series that organic chemists use, because it's the only one that actually tells you the structure. Okay, which is awesome. So then, because there's such a need for regulation and getting to know bigger and bigger structures and natural products, and it turns out that there is this phenomena in an awful lot of nature. This is an ongoing study that is always growing. Starting in 1984, a whole new round of vocab came out. This phenomenon is called a stereoisomer and stereocenter. So even though we may have a million vocab terms because of the 150 years of research, almost 200 years of research, we are going to go with the modern vocab. Okay, let's actually just spell out vocab, and then we're going to put it into perspective. So vocab started with things like polarized light and optical activity, because it was something that they that they could gauge. Oh, I think I better spell activity right. It was something that they could actually see. There was something that was different, and we're going to spell that out in our isomers. So anytime you're reading in stereocenters and stereoisomers and you see a plus or a minus, so go look at an EpiPen. You'll see a plus or a minus out in front of the name. Plus or minus only tells you optical activity. It does not tell you 3D structure. The same with little l and little d. They are connected to optical activity. That is lever rotatory, dexter rotatory. It does not tell you structure. Okay, this is our earliest vocab. You still see it used today, but it doesn't actually tell you which compound is what. Then came the idea of chirality. And that is that right hand and left-handedness, okay? And then the idea of that sp3 tetrahedral has been around for a while, but it hasn't really been connected until more modern times to that structure and what that really means. So even though it's been there for a while, we're gonna keep it. And that Vant Hoff rule came out really early, but we actually tweaked it and are going to use it modern times. Okay, then as we went from wine to sugars and amino acids, these are some of the first that were studied past our wine. We got into the Fischer projections. Those were L and D, big L, big D. Those are for Fischers. They only work for amino acids and sugars. So if you see that, that only reason that works is because they have a set rule for sugar and amino acids. And then we had this idea of a racemate or racemic mixtures of 50-50. And then because of those terms from Vant Hoff and asymmetry, and then leading into Calvin and chirality, there's a whole lot of vocab calling things an asymmetric center or asymmetry or a chiral center. All of these are going to end up meaning the same thing. Erythro and threo, these are specifically from sugars. All of these are popular before about the 1960s. You'll still see them in literature, but they are following the history of our stereo center. And then as we get modern, past about the 1980s, 1960s to 1980s, now what we are major concerned with is a 3D structure. So we can actually know which molecule does what. We are concerned with mirror images. Taking that sp3 carbon, we've branched out to whole molecules. And even bigger, we have gotten into something called a %EE. Let's describe that in just a second. And we're, of course, going to use that RNS system starting from the 1960s. So the vocab I will be focused on will be a lot of this. Okay, we're still going to see all that older vocab. They're all meaning very similar things. Let's put it into our isomers table. All right, we've got constitutional. We've got conformational. And then here's where we're growing, configurational. All right, you guessed it. What are we looking at? We're looking at an arrangement in space. All right, in the last 50 years, this is where we're growing. So let me grow this isomers. Configurational. Let's get modern. Configurational isomers are broken into two sets. That first set is mirror images. Those mirror images are literally our right hand and our left hand. We have mirror images possible when we have an sp3 carbon with 4 different groups attached. Now, our next video is going to get deep with this. What do we call it when we have mirror images? These mirror images are called enantiomers. Enantiomers are only mirror images. These are configurational isomers. Configurational isomers has a general tab here. We have stereoisomers. We have 2 kinds. Mirror images is one kind. All others is the other kind, and they are called diastereomers. So things like cis and trans are diastereomers. So why do we care about our isomers and our configurational isomers? And then we'll stop this video and make all of this practical. How do we apply this to our compounds? So why do we even care about our isomers? Our mirror images, what has made them so mysterious for over 200 years is that they have the same properties. What? Shut the front door. It turns out that the only properties that are different for mirror images is rotating light. Our diastereomers have completely different properties. They are completely different molecules. Cis and trans will have different boiling points. They'll have different energies. We've looked at that in our last unit. But our mirror images have been a mystery for 250 years because they have the same properties. So it wasn't actually until the early 1800s when chemists and physicists really liked their wine and started noticing, holy crap, these structures can actually rotate light in 2 different directions, that anybody even knew that mirror images existed in nature. And even bigger, it wasn't until the 1960s then that we understood, holy crap, we really need to know this because they are preferenced. There are different preferences in nature for those mirror images. So things like amino acids in your body prefers the L-amino acid. Your body prefers D sugars. So if you get sugar from a natural source, it's going to rotate light. If you get sugar from a lab, it isn't, because you've got a 50-50 mixture. So it's actually a really, really evolving story. Thank you for letting me just show all this vocab in one video. And now let's take all of this and apply it to our organic chemistry